we continue looking at the basics of electricity. Let's now look at magnetism. Now, magnetism is related to electricity because in the motor you have a magnet. In small motors it's a permanent magnet. In larger motors it's an electromagnet. And the reason why the motor turns is because of the interaction between the magnetic fields of the rotor, the part that rotates, and the stator, the part that is stationary. In the generator, you have either a permanent magnet for small generators or an electromagnet for larger generators. Then when the rotor spins, these two magnetic lines of flux between the rotor and the stator field cut each other and induces a voltage. So magnetism is very important when it comes to electricity. The use of electricity in the rotor or in the motor, and the generation of electricity in the generator. Now let's go. The principles of magnetism are an integral part of electricity. Electromagnets are used in some direct current circuits. Alternating current cannot be understood without first understanding magnetism. Types of magnet. The three most common forms of magnets are the horseshoe, this one in the shape of a horseshoe, bar, this one in the middle, and the compass needle. Right. All magnets have two characteristics. They attract and hold iron. If free to move, like the compass needle, the magnet will assume a roughly north-south position. Well, that's because the earth itself has iron in the center, which has its own magnetic field, or is affected by magnets. Or what happened, the iron in the center of the earth, it creates its own magnetic field. And it was discovered long time ago that if you hang a magnet so that it is free to rotate, it will always assume a certain direction, roughly north-south direction. So that is used to find direction. Now, magnetic lines of flux. Every magnet has two poles, one north pole and one south pole. As you see here, N for north, S for south. Invisible magnetic lines of flux leave the north pole and enter the south pole, that is outside of the magnet. While the lines of flux are invisible, the effects of magnetic fields can be made visible. When a sheet of paper is placed on a magnet and iron filings loosely scattered over it, the filings will arrange themselves along the invisible lines of flux, as you can see here. By drawing lines the way the iron filings have arranged themselves, the following picture is obtained. This picture. Broken lines indicate the path of magnetic flux lines. The field lines exist outside and inside the magnet. The magnetic lines of flux always form closed loops. So you see, there's no break in the loops. They go round and round from north go outside the magnet, go around and enter the south. Inside the magnet, they go from south to north and go right around. Magnetic lines of flux leave the North Pole and enter the South Pole, returning to the North Pole through the magnet. Interaction between two magnets. When two magnets are brought together, the magnetic flux field around the magnet causes some form of interaction. Two unlike poles brought together cause the magnets to attract each other. As you see at the top here, when you have a north and south pole of two magnets brought together, they attract. Two unlike poles brought together cause the magnets to attract each other. Here, two like poles brought together cause the magnets to repel each other, as you can see down here. When you have two south poles or two north poles brought together, the magnets repel each other. Now note, the magnetic lines of flux do not cut across each other, but they can be bent out of shape like a spring blade. Now we look at electromagnetism. Now the fact is, anytime a current flows through a conductor, a magnetic field is set up around the conductor. Whatever type of conductor, no matter how high or low the current is, there's always a magnetic field set up around the conductor. The left-hand rule for conductors. An electromagnetic field is a magnetic field generated by current flow in a conductor. Whenever current flows in a magnetic field exists around, whenever current flows, a magnetic field exists around the conductor. Every electric current generates a magnetic field. A definite relationship exists between the direction of current flow and the direction of the magnetic field. The left-hand rule for conductors demonstrates this relationship. If a current carrying conductor is grasped with the left hand with the thumb pointing in the direction of electron flow, the fingers will point in the direction of the magnetic lines of flux. So the magnetic lines of flux whirling around and round the conductor. Now, if you look in some books or look at some websites, they will not talk about the left hand rule. What they will talk about is the right hand rule, and they will call it the right hand grip rule, because you're gripping the conductor. The reason is because this document concentrates on the flow of electron. Other documents might concentrate on the conventional current flow, which is in the opposite direction. So instead of gripping it with the left hand, they grip it with the right hand, because the flow of current will be not from left to right as in this diagram, but from right to left. It's considered right to left, even though the electrons are actually flowing in this direction from the negative through the wire, through the circuit, to the positive of the source. Conventionally, they consider current flowing from the positive through the circuit to the negative of the source, whether it's a generator or a battery. Now, current carrying coil. A coil of wire carrying a current acts like a magnet. Individual loops of wire act as small magnets. So you wrap the wire in the form of a coil. In this case, you have a coil. Here, the strength of the field can be increased by adding more turns to the coil. The strength can be increased by increasing the current. So a coil of wire carrying a current behaves as a magnet. Left-hand rule for coils. A left-hand rule exists for coils to determine the direction of the magnetic field. The fingers of the left hand are wrapped around the coil in the direction of the electron flow. As you see here, the thumb points in the direction of the north pole. As you can see here. So you have the north at one end and the south at the other end. Electromagnets. An electromagnet is composed of a coil of wire wound around a core. The core is usually a soft iron which conducts magnetic lines of force with relative ease. So the magnetic lines of force will concentrate themselves in the iron instead of being widely scattered around in the air. When current is passed through the coil, the core becomes magnetized. The ability to control the strength and direction of the magnetic force makes electromagnets useful. So the electromagnet, it becomes a magnet only when current flows through it, and it is applied in cranes that are used to lift iron. When the operator turns the magnet on, iron jumps onto it. The operator can now lift the crane, turn it in a direction or over a certain location, switch off the current, and the iron will fall at that location. Now, as with permanent magnets, opposite poles attract. An electromagnet can be made to control the strength of its field, which controls the strength of the magnetic poles. A large variety of electrical devices such as motors, circuit breakers, contactors, relays, and motor starters use electromagnetic principles. And another application that comes to mind is the door lock, the power door lock for the car. It uses an electromagnet. Let us review. The rate at which work is done is called. I want you to place the answer in the comment section. The basic formula for power is in a circuit with a 12-volt supply and a 4 ohm resistance, what is the power consumed in watts? The two characteristics of all magnets are they attract and hold what type of material, and if free to move will assume roughly in what direction. And you're talking about the compass needle in this case, right? So they will hold a certain position. Lines of flux always leave which pole and enter which pole. So you should remember that. The left-hand rule for conductors states that when the hand is placed on the current carrying conductor with the well, you know what you have on your hands already. Pointing in the direction of the electron flow, the fingers will point in the direction of what? Okay, so that's our review there. The next thing we're going to look at is an introduction to AC. Let us do that in a separate video. So I will see you in the next video.